Welcome to the Extraordinary 10 podcast, the place where the most magnificent and mind-bending facts in existence are explained to you in vivid detail.
Today, we are embarking on a massive journey. We've researched 10 extraordinary facts about the limits of reality and the nature of existence.
And we aren't just giving you a list, we are diving deep into the science, the mystery, and the why behind these wonders.
And we're talking about the universe's origin, its ultimate fate, and our place in it. It's a journey that really challenges your fundamental understanding of space and time.
It really does. So if you love exploring the unknown, don't forget to share this deep dive with a friend and subscribe to the channel.
It's the best way to support the show and ensure you never miss a deep dive.
All right, are you ready to see the world differently?
Let's start the clock.
Here is fact number 10.
Fact 10. Welcome to the Extraordinary 10 podcast. Today we begin our journey. Let's start the clock with fact number 10. And fact 10, well, it's a monumental one. We are diving into what you could call the ultimate remnant of creation, the cosmic afterglow. For you, the listener, we're going to unpack this idea that this light, the cosmic microwave background, isn't just a discovery. It is literally the oldest photograph of the universe we will ever have.
And that framing is, I think, perfect. Our mission today is to take this abstract idea, the CMB, and make it real.
Right.
We want to get a handle on what this faint hum actually is, how we even measured it, and maybe most importantly, why this ancient light sets the ultimate limit on what we can see.
It's a boundary.
It's the boundary of our knowledge in a very real sense.
You know, when you talk about boundaries in ancient light, it sounds like something straight out of science fiction. But what I love is that we can start with something so simple, so relatable.
Radiostatic.
Radiostatic, exactly.
It's honestly the best way in. If you take an old radio and you tune it right between the stations, you get that hiss.
That familiar shh.
Yeah, that sound. Now, most of that is pretty mundane stuff, local interference, signals from Earth, noise from our own galaxy.
But our sources all point to this tiny, tiny fraction of that noise being something else entirely.
Exactly. About 1%, just 1% of that random noise you hear is the actual honest-to-goodness energy, the light from the Big Bang.
Hold on, I have to pause on that. 1%.
1%.
So if I'm hearing that static, 1 out of every 100 of those energy packets is from the dawn of time.
It's light that's been traveling for 13.8 billion years, and it's hitting your antenna right now, or just passing through you.
That makes it so much more tangible.
Yeah.
And the story of its discovery, it wasn't some grand search, was it?
Not at all. It was 1964. Two astronomers, Penzias and Wilson, were trying to get a new antenna working, and they kept picking up this annoying, persistent hiss no matter where they pointed the thing.
I remember reading that they thought it was pigeons, right?
They did. They cleaned out pigeon droppings, they rechecked all the equipment, they assumed it was some kind of contamination.
But it wasn't.
It wasn't noise, it was the universe. It was this faint thermal echo of the entire cosmos, which is where the idea shifts from just noise to something like heat.
Okay, so let's go there. Let's move from the radiostatic to the actual science. If you could just float out in deep space, far from any stars, what would you feel? Or what would you measure?
You'd measure a faint hum of microwave radiation, and the key thing, the thing that's so precise, is the temperature. It averages 2.725 degrees above absolute zero.
Just a tiny bit above the coldest possible temperature.
Just a hair's breadth. That is the temperature of space itself.
So help me understand this. Are we looking at an object that's 2.725 Kelvin? Or is this something different?
That's a great question, and it's a critical distinction. You're not looking at a thing. You're detecting the heat signature of the whole universe, but from a very specific moment in its past.
It's everywhere.
It's everywhere. It's isotropic, meaning it looks the same in every direction. It's like you're surrounded by the glow of a giant ancient ember that has cooled to almost nothing. You're looking back through time.
And this is where that amazing analogy comes in. To understand why we see this light at all, we have to talk about the early universe being opaque.
Right. The concert hall filled with fog.
Let's unpack that. The concert hall filled with this incredibly thick fog.
Okay, so imagine it. That fog represents the universe in its first 380,000 years.
And what was that fog made of physically?
Primordial plasma. It was unbelievably hot, over 3,000 Kelvin, so hot that electrons and protons were just flying around. They had way too much energy to actually bond and form stable atoms.
So chaotic, electrically charged soup.
A perfect description. And in that soup, in that fog, photons, particles of light, were completely trapped.
Oh.
Well, a photon couldn't go more than a tiny distance without slamming into a free electron and getting scattered off in a random direction.
So light couldn't travel in a straight line.
It couldn't travel at all. The universe was effectively opaque, a blinding, chaotic furnace. You couldn't see anything because light couldn't get from point A to point B.
Okay. But the universe was expanding this whole time.
It was. And expansion means cooling. And
Yeah.
as it cooled, it was approaching that critical threshold.
The 3000 Kelvin mark.
Exactly. That is the pivotal moment. As the temperature dropped below that, the electrons and protons slowed down just enough for them to finally stick together.
They formed the first stable atoms, hydrogen and helium.
This is a process called recombination, and the second it happened, the fog vanished.
Just like that.
In cosmic terms, yes, instantaneously.
Yeah.
Because once those electrons were bound up inside atoms, they weren't free to scatter the photons anymore. And suddenly, all that trapped light had a clear path.
It was released.
In one massive, universe-wide flash. That flash is what we now see as the cosmic microwave background.
And that explained the huge temperature drop you mentioned. It was released as a searing 3000 Kelvin light, but we see it today as a frigid 2.725 Kelvin.
Right, and that's because of redshift. The universe itself has been expanding for 13.8 billion years.
And that expansion literally stretches the light waves.
It does. Imagine a wave drawn on a rubber sheet. As you stretch the sheet, the wave gets longer.
Longer wavelengths means lower energy.
And lower energy means a lower temperature. The light didn't cool down on its own. The very fabric of space stretched it from a visible glow into the microwave spectrum we detect today.
So our detectors are basically time machines.
They're like time machine microphones picking up the universe's first cry, just massively redshifted.
Okay, here's where, for me, it gets really mind-bending. When we finally mapped this background light with satellites like Planck, it wasn't perfectly smooth.
No, it wasn't, and thank goodness for
I
that.
had these tiny, tiny temperature fluctuations.
Those fluctuations are everything. I mean, they are the reason we're here having this conversation. Without them, the universe would just be a boring, featureless haze of gas forever.
How small are we talking?
The variations are minuscule, about 1 part in 100,000. Some spots are just slightly warmer, some slightly cooler.
And our sources call these the seeds of everything. What were they physically?
So we trace them all the way back to quantum ripples. In the first fraction of a second, just random quantum energy fluctuations got blown up to enormous scales during cosmic inflation.
And by the time the fog cleared 380,000 years later, those ripples were actual differences in density.
Yes, the slightly cooler spots were areas where matter was just infinitesimally denser than average.
And gravity, which is patient, saw those denser spots and went to work.
It's the patient architect. It just started pulling material into those slightly denser regions. Over millions and billions of years, those tiny seeds grew into the galaxies and the great cosmic web we see today.
So you can literally draw a line from the structure of the universe now, every galaxy, every star, every atom in your body, all the way back to a specific tiny ripple in that baby picture of the universe.
It's the cosmic blueprint, and that blueprint is so detailed that it tells us what the universe is made of.
How does a map of hot and cold spots do that?
Well, the exact size and spacing of those ripples are dictated by the physics of that early plasma. By analyzing them, we can basically conduct a cosmic audit.
And what did that audit find?
It confirmed our strange reality. Only about 5% of the universe is normal matter, the stuff we're made of.
The other 95%.
About 27% is dark matter, and a whopping 68% is dark energy, the thing driving the accelerating expansion. The CMB is how we know those numbers.
Wow.
But this all leads to the unsettling part of the story. The CMB isn't just a picture. It's a wall.
An opaque wall in time.
Precisely. It's the surface of last scattering. We can't see past it with light.
So you're saying we can't just build a better telescope? We are fundamentally blocked from seeing what came before.
We are, because the universe itself was the light blocker. The CMB is the light that was released when it stopped being a wall. Anything before that 380,000 year mark is hidden from us.
So we can't actually see the Big Bang itself? We can't see the details in inflation?
Nope. The analogy one source used was perfect. We're looking at the oldest photo possible, but the film started rolling only after the opening credits had already finished.
That's a powerful way to think about it. It answers so many questions, but it leaves the biggest ones, well, unanswered.
It permanently reminds us of the mysteries that are just out of reach, which is why cosmologists are now looking for other ways to peek behind that curtain.
Messengers other than light?
Exactly. Things like gravitational waves and primordial neutrinos. They weren't blocked by that plasma fog. they could, in theory, let us see much, much earlier.
So if we could detect those primordial gravity waves, could we see evidence of something like the multiverse? Or what happened in the first second?
That is the ultimate goal. The CMB shows us the universe at 380,000 years old. Gravitational waves might show it to us at a trillionth of a second old.
But until then, this is it. This is the boundary.
It is the definitive record, the starting point for everything we see, and the final word on what we can see.
What a place to end for Fact 10. The CMB is the seed of all structure. It's the recipe for the cosmos, and it's the ultimate barrier, showing us precisely where our knowledge ends.
And just remember that perspective. You, right now, are being bathed in this light. The afterglow of creation, 13.8 billion years old, is passing through you as you listen. It's a constant physical connection to the beginning.
That was Fact 10. Stay tuned, Fact 9 is coming up next.
Welcome back. We are moving right along in our countdown. Let's dive into fact number #9. Today we're tackling supermassive black holes, or SMBHs, and for a long time we've thought of them as, just cosmic vacuum cleaners, pure destroyers.
Right, the ultimate villain.
Exactly. But the sources we've been digging into paint a completely different picture. They're not just destroyers, they're the engines at galactic cores.
And that's really the mission for this deep dive. We want to get you past that sensational, fearful image of black holes and into their essential role.
Which is what exactly?
They're architects, proactive architects of galactic structure. I mean, think of them as the gravitational foundation the entire cosmos is built on. And this is the big thing. They expose the deepest paradoxes in physics we're facing today.
So how are we going to break this down for everyone?
We've got it in 3 parts. First, a detailed visualization. A trip, a pretty harrowing one, toward the event horizon of our own Milky Way's monster. Second, we've got a powerful analogy to help you grasp how they control a whole galaxy. And finally, we're going to tackle the biggest unsolved question in all of physics, which is centered right on these things.
All right, let's start with that visualization. We're heading to the center of our own galaxy, Sagittarius A, SGRA for short.
26,000 light years away.
So as you get closer, you're looking for an object that has the mass of 4 million suns, but it's squeezed into this tiny, tiny space.
And the hole itself, the actual black hole, is just a sphere of perfect blackness.
And how big are we talking?
Cosmically, it's pretty small, only about 20 astronomical units across.
So to give everyone a sense of scale, that's about the distance from our sun out to Uranus.
Exactly. And that sphere, that's the event horizon. It's a region of empty space-time you can enter, but you can never, ever leave.
But here's the wild part. You wouldn't even see that black sphere, would you?
Not directly, no. The real power, the thing you see, isn't the hole itself. It's the absolute chaos erupting around it. You're looking at a maelstrom of light, the accretion disk.
Which is what, exactly?
It's the final scream of everything SGRA has shredded. I mean, shattered stars, gas, dust, all of it. And it's glowing blue-white at millions of degrees.
Millions.
Oh yeah. The friction and the speed are what make it so incredibly bright.
And this material isn't just swirling around gently, it's accelerating, right? Moving at a huge fraction of the speed of light just before it vanishes over the edge.
A significant fraction, yeah. And the weirdness starts way before you even get there. As you get closer, the effects of general relativity just become obvious.
Like time dilation?
Exactly. Your watch would literally tick slower than a friend's watch who stayed behind in safer space.
So if I took a quick trip, say, for an hour of my time and then came back, how much time would have passed for them?
It totally depends on how close you got. It could be minutes, hours, maybe even days.
Wow.
Yeah, just shows you how deeply the black hole warps reality. Space and time aren't separate things anymore. They're twisted together by gravity.
And this power goes way beyond just messing with time locally. A lot of these SMBHs are spinning, right?
Near maximally, some of them. And when they do, they generate these 2 opposing, super-focused beams of plasma, the jets.
And these jets are huge. We're not talking about something that stays inside the galaxy.
No. They're like cosmic lighthouses. They can stretch for millions of light years into the space between galaxies, blasting out at almost the speed of light.
Okay, so that really gets to the engine idea, but where does all that energy come from? It's not like it's burning fuel.
That's the unbelievable part. It's not. It's powered by the rotational energy of space-time itself.
Say that again?
The black hole's magnetic fields twist the fabric of space-time like a giant spring, and when that spring snaps, boom, it releases all that energy as these massive jets.
That sounds incredibly efficient.
It makes our attempts at nuclear fusion look just hopelessly wasteful.
How so?
Well, fusion, like in our sun, converts less than 1% of mass into energy. This process. When a spinning black hole makes these jets, it can convert mass to energy with an efficiency approaching 40%.
40%? That's insane!
It's physics on steroids. It's why the brightest things in the universe, quasars, are so bright. It's just a galaxy with a supermassive black hole at its center that's actively feeding.
Okay, so now that we have the mechanics, let's scale up. This brings us to that analogy you mentioned from the source material.
Right.
Supermassive black hole as a cosmic drain at the bottom of a bathtub.
Yeah, and the tub is the entire galaxy, all the gas, dust, stars, that's the water.
Yeah.
But this drain is so powerful, it doesn't just suck things down.
It heats the water
to millions of degrees, and that heat creates those geysers, the plasma jets, that shoot millions of light years into space.
Hold on, that's where the analogy feels a little tricky to me. A drain pulls things in. How can it also be shooting geysers of energy out?
That's a great question. And it's because it's not a simple drain. It's an engine. It uses the energy of the stuff falling in to power the stuff going out. And that outflow, those jets, are crucial.
Crucial for what?
For managing the galaxy. They blast all this thermal energy into the gas clouds surrounding the galaxy, what's called the galactic halo.
And what does heating up that gas do?
Well, if the gas can't cool down, it can't clump together. And if it can't clump together,
new stars can't form.
Exactly. The black hole acts like a cosmic thermostat. It stops the whole galaxy from just burning itself out in one giant runaway fire of star formation.
So it's literally regulating the life cycle of the entire galaxy.
Over billions of years, yes. It dictates the size, the shape, the pace of evolution. SGRA is the reason the Milky Way looks the way it does.
It's just amazing that this one invisible point can control billions of stars. It's like a silent conductor for a symphony it can never be seen performing.
And that invisibility, that singularity at the core, leads us right to the biggest problem in physics.
The black hole information paradox.
That's the one. It's simple to ask, but it completely devastates our understanding of reality. What happens to the information that falls into a black hole?
It's just vanished forever.
Or is it some preserved?
Now, this sounds kind of philosophical, but it's a real physics problem, right? Why is information so important?
Because in quantum mechanics, information is just as fundamental as energy or mass. You can't just destroy it. Every physical process has to be reversible. If you run the movie backwards, you should be able to see exactly how it started.
A balanced ledger for the universe.
A perfect one. Quantum mechanics demands that the books always balance. But general relativity, Einstein's theory that describes black holes, says the opposite.
It says once something crosses that event horizon, the information about it is just gone. Wiped from the universe forever.
And this is where it gets really interesting. Black holes force this direct, head-on collision between our two best theories of the universe.
General relativity for the big stuff, quantum mechanics for the small stuff.
And they give completely contradictory answers right at the event horizon. One has to be wrong, or at least incomplete.
So if information really is lost,
then quantum mechanics is fundamentally broken. We have to start over. If it's preserved, maybe on the surface of the event horizon, then our understanding of gravity is wrong.
So the SMBH is basically the ultimate laboratory.
It is. Until we solve this, we don't truly understand what space-time is, or what reality is made of.
And beyond the physics, there's this huge existential angle. These things aren't just weird accidents. Every big galaxy has one.
They're fundamental.
So what does this all mean for you, listening to this?
Well, without these SMBHs regulating things, stopping that runaway star formation, the universe would be a chaotic mess.
Galaxies would just burn out. There'd be no stable, long-term environment for, things to evolve.
So the stability that SGRA has provided our Milky Way is what allowed our sun to grow old and for life to emerge here on Earth.
In a really strange way, we owe our existence to this 4 million solar mass monster. It's our guardian, providing the structure we need. And it's our potential doom if it ever gets hungry again.
So to sum it all up, supermassive black holes define our reality. They're not just destroyers, they're the engines that build structure, and they force us to confront the absolute limits of our own understanding.
They're essential, they're terrifying, and they are completely incomprehensible all at once.
A true paradox. And here's one final thought to leave you with, building on that information paradox. What if the solution is something called the holographic principle?
Okay.
The idea that all the 3D reality that falls into a black hole gets perfectly encoded on its 2D surface, the event horizon. If that's true, How does that change how you see reality versus information? What if our whole 3D universe only seems real because the information on some distant boundary is making it so?
Something to think about next time you look up at the stars. That covers fact #9. Ready for the next one? Let's head to fact #8.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 8. So today's topic is dark energy. And honestly, this one might just be the most consequential, maybe the most unsettling fact about our reality.
It really is.
I mean, we're talking about the engine of the universe, the thing that makes up, what, 68% of everything? And we're almost totally clueless about what it actually is. So our mission for this deep dive is to get a handle on not just what dark energy is doing, which is, expanding the universe, but why its existence creates this kind of existential terror.
It's the ultimate cosmological shock. For generations, the whole paradigm, really stemming from Einstein's work, was that gravity ran the show.
Right. Gravity was the brakes.
The great cosmic braking system, exactly. We thought the immense pull from all the matter, all the dark matter, it had to be slowing down the expansion from the Big Bang.
We assumed it would either, coast to a stop or maybe even collapse back in on itself. The big crunch.
Precisely. But then came the late 1990s. We started observing these very distant supernovae.
And they act like cosmic mile markers, right?
Perfect cosmic measuring sticks. And what they showed us just defied every single expectation. The universe wasn't slowing down, not even a little bit.
It was accelerating.
It was, and it is accelerating, speeding up. And that one discovery, it just flipped the whole script. It demanded that there had to be some kind of repulsive anti-gravitational force, dark energy.
Okay, let's unpack this. The sources use a great visualization. Let's say you're standing on a cosmic observation deck. You're looking out.
Okay.
You see all these distant galaxies, like ships on an ocean. Now, gravity, that's the anchor, you should be slowing them all down. So what are we actually seeing from that deck?
We're seeing something that completely breaks from, standard physics on that scale.
Yeah.
Those ships, they aren't slowing down, they're accelerating. And the farther away they are, the faster they're moving away from us. It's like there's this invisible wind just constantly pushing them. But we have to be really, really precise about what that pushing actually is.
Yes, because this is the mind-bending part.
Yeah.
It's not that the galaxies are flying through space faster and faster.
That's the crucial distinction. Yeah, if they were just moving through space, they'd hit a speed limit, right? The speed of light.
Right.
But that's not what's happening. The acceleration is coming from the fabric of space itself being manufactured. Created out of nothing between us and that distant galaxy.
So the space itself is inflating, like a balloon.
An invisible balloon, exactly. It's constantly creating more distance between any 2 points that aren't gravitationally bound together.
And the immediate implication of that is just staggering. If this keeps up, what happens to all those galaxies we can see right now?
They slide away into darkness, they vanish. See, dark energy doesn't just push, it creates a horizon, a barrier we can never cross.
So any galaxy cluster that isn't already part of our local gravitational neighborhood?
It's doomed, from our perspective anyway. As the expansion speeds up, they accelerate away toward a point where their light will simply never reach us again.
So even if they sent out a beam of light right now, pointed at us,
by the time that light travels, so much new space will have been created in front of it that it will never, ever close the gap.
we are literally watching the universe thin out, separating into these isolated little islands of matter.
We're watching the universe commit what some have called slow-motion suicide. It's being torn apart by this invisible energy field we can measure. We know it's 68% of everything, but we have no idea what the engine itself actually is.
Let's get into the mechanics of that.
Yeah.
I like the analogy of a cosmic tug of war. So on one side of the rope, you have the anchors.
Right. That's regular matter and dark matter. They use gravity to pull everything inward, trying to slow things down.
And on the other side,
You have dark energy, this pure outward stretching force. And what makes it a completely unfair fight is how each side reacts when the universe expands.
and this is where the timeline gets really interesting. For a long time, gravity was actually winning. But then, around 7.8 billion years after the Big Bang, the balance of power shifted. Why then? What happened?
It all comes down to density. Gravity's strength depends on how close matter is together. So as the universe gets bigger, the volume increases a lot.
So the matter and dark matter get spread out, diluted.
Exactly. Their density just plummets. And over time, their gravitational grip gets weaker and weaker.
But dark energy, it doesn't follow those rules.
Not at all. And this is the core of the mystery. The leading theory is that dark energy is a property of empty space itself, vacuum energy.
So you get more space.
You get more dark energy, its density is constant, it never ever dilutes.
Okay, let me just make sure I'm getting this, and for everyone listening. Gravity strength gets weaker because its source matter gets spread thin.
Correct.
But dark energy strength stays the same per unit of space. So when space expands, it's not watering down the dark energy, it's literally creating more of it in that new space.
That is the perfect way to put it. For the first 7.8 billion years, matter was still dense enough to win the tug-of-war even while it was diluting. But there was a tipping point.
The moment its density dropped below the constant density of dark energy.
And that was it. The fight was over, dark energy started winning, and because it never dilutes, it will never stop winning. The other side doesn't stand a chance in the long run.
So the end game of this tug-of-war is just irreversible separation. The end of the universe isn't some big fire or ice scenario.
No. The predicted outcome, if this holds, is what the sources call profound expanding loneliness. Every galaxy outside our own little local group gets pushed away so fast its light just stops reaching us.
Gone. Effectively impossible to ever see or interact with again.
They might as well not exist.
Which brings us squarely into the existential terror part. This stuff is 68% of the universe, and we have no idea what it is. What are the theories?
Well, there are two main ideas, and they're both pretty unsettling. The first is probably the simplest, but also the most profound. It's Einstein's cosmological constant.
Okay.
This idea says that dark energy is just a property of space, a fixed intrinsic energy density of a vacuum. Nothingness isn't empty, it has energy, and that energy pushes things apart.
The vacuum of space itself is the engine.
The engine of cosmic acceleration, yes.
What's the second possibility?
The second is that it's something dynamic, a field that could change over time, sometimes called quintessence.
Which could mean what?
Well, if it got stronger, you could get a big rip. The expansion accelerates so violently that galaxies, stars, planets, even atoms get torn apart. If it weakened or reversed, you could get that big crunch we talked about.
But the evidence doesn't point that way, does it?
No. All of our best data, from the Planck satellite, from galaxy surveys, it all points very strongly to the simplest, most constant explanation.
A cosmological constant.
Yes, the unchanging energy of empty space.
And if that's true, the long-term future for science, for discovery, it's an absolute tragedy.
It is the ultimate cosmic erasure. Think about an observer in our galaxy, say, 1 trillion years from now. By then, the accelerating expansion will have stretched the light from every single external galaxy.
Andromeda, everything.
All of it, stretched the wavelengths so dramatically that they become impossibly long.
Let's pause on that. Red shifted into complete invisibility. What does that physically mean for the light?
So, redshift is light waves getting stretched as the source moves away. With acceleration, that stretching becomes extreme. Visible light gets stretched past red into infrared, then microwaves, then radio waves with almost no energy.
So for that observer, 1 trillion years from now,
For them, that light would be so stretched, so diffuse, they just couldn't detect it. Even with technology we can't even imagine.
the sky just goes dark,
Yeah,
empty.
it gets worse. They also lose the single biggest clue to our origins, the cosmic microwave background.
The echo of the Big Bang.
That radiation would also be stretched into total undetectability, so a future civilization, no matter how advanced, would look out and see nothing, just their own local island galaxy. They would have zero evidence the universe ever expanded.
They would have no idea the Big Bang even happened.
They'd conclude their galaxy was the entire universe, static and alone. They'd be completely ignorant of the 13.8 billion years of cosmic history that we can see today.
Wow, so dark energy isn't just deciding the future of the universe.
It's actively erasing the past. It's erasing its own evidence. We are living in this very brief, privileged moment, a golden age where the full picture is still visible. In the future, that history becomes an unrecoverable mystery.
That's a staggering thought. The force that's driving this incredible expansion is, at the same time, hiding its own origin story from anyone who comes after us. We're in this unique window of opportunity for discovery.
And that leaves a final, pretty profound question for you to think about. If dark energy really is just a property of empty space, an energy of the vacuum itself, what does that say about what a true vacuum is? And maybe more practically, could we ever hope to detect that tiny bit of energy right here on Earth in the empty space of a lab? That's where the biggest thing in the universe meets the smallest scale of quantum physics.
That covers 8. Ready for the next one? Let's head to fact 7. Welcome back. We are moving right along in our countdown. Let's dive into fact number 7.
This one. This is where things get really counterintuitive.
It really is. This fact, it just immediately slams into one of the most fundamental rules of physics. It creates this massive cosmic contradiction that seems, well, utterly impossible.
It really does. I think this is the one that forces a complete intellectual reset for almost everyone who learns it. You know, you grow up knowing that nothing can travel faster than light.
300,000 kilometers per second. It's the ultimate speed limit.
Exactly. It's supposed to be the law. But when you look at the universe as a whole, it looks like everything is violating that rule.
Okay, let's lay out the paradox for you. Cosmologists are very, very confident that the universe is 13.8 billion years old.
Right.
That means the oldest light we can possibly detect has only had 13.8 billion years to travel across space and, reach our telescopes.
Simple enough. So you'd assume the edge of what we can see is 13.8 billion light years away.
You'd assume that, but it isn't.
No. That would only be true if the universe were static, if space itself wasn't changing size. But because space is stretching while that light travels,
The actual distance is it's mind-blowing.
the current distance to the matter that emitted that oldest light isn't 13.8 billion light years. It's 46.5 billion light years away in every single direction.
46.5 billion. That creates an observable sphere that's, 93 billion light years wide? The raw numbers just don't check out.
They don't seem to.
So how did light travel 46.5 billion light years and only 13.8 billion years? I mean, did Einstein get it wrong?
He didn't, and that's why our mission today is so critical. We need to unpack this temporal mismatch. We're going to show you how the mechanics of expanding space create this profound, invisible cosmic bubble that confines everything we can ever know.
And how that bubble is really built by the movement of space, not movement through space.
Exactly.
Okay, so let's start by clarifying those cosmic numbers. We have the travel time, 13.8 billion years.
Right, and then we have the current actual distance, the 46.5 billion light years.
And that edge, that 46.5 billion light year line, has a name, doesn't it?
Yes. Astronomers call it the particle horizon. It's the boundary of the region from which light particles, photons, have had enough time to reach us since the Big Bang.
Which brings us back to the crucial question. If light speed is the absolute limit, how did light cover that much bigger distance?
And the answer is it's so central to all of modern cosmology. The light itself never violated the speed limit.
It didn't break the rule?
Never. It always traveled at the speed of light relative to the local space it was passing through. What happened is that the matter that emitted the light has since moved much, much farther away.
Because the space between us and it stretched.
It stretched a lot.
Okay, let's unpack this distinction, because this is where physics can start to feel like it's playing tricks on you. Can you give us that visualization, the one that clarifies movement through space versus movement of space?
Of course. Let's use the runner analogy from the sources. It's really helpful. Imagine a runner starts a race standing 100 meters away from you.
Okay, got it.
As they start running, they fire a flare. That flare is the light. Now, and this is the crucial part, the ground beneath them is like a gigantic cosmic treadmill, and it's accelerating backward, away from you.
So the runner, which is our distant galaxy, isn't actually moving that fast on the treadmill itself, but the treadmill is carrying them away.
Precisely. The light flare leaves the runner and starts its journey toward you, traveling at the speed of light. It's respecting the local speed limit. But every single inch of space it crosses is stretching out behind it.
So it's like it's swimming against a current.
A constantly strengthening current of expanding space. Yes.
And the result is that the light takes that full 13.8 billion years to finally reach our eyes.
But in all that time, the source, the runner, the galaxy that shot the flare, has been passively carried away by all that stretching space, and now it's at that incredible current distance of nearly 47 billion light years.
So that distinction is everything. Movement through space is what's limited by Einstein's relativity.
But the movement of space itself, the stretching of space-time's fabric, that's not bound by the same speed limit at all.
So let me just push on that idea.
Yeah.
Are you saying that right now the space between us and that distant galaxy is expanding at a rate faster than the speed of light?
Yes.
And that's allowed?
That is fundamentally allowed, and that's where the paradox just resolves itself. Relativity states that objects within space-time can't move relative to each other faster than light. But it places no constraint on how fast space itself can expand.
The most extreme example of that being the inflationary epoch, right after the Big Bang.
Exactly. Moments after the Big Bang, space expanded exponentially faster than light. That's why everything got so far away from everything else so quickly.
Okay, that makes the 46.5 billion light-year figure feel, well, less mysterious anyway. It's the result of that initial inflation plus 13.8 billion years of continuous stretching.
It does. And it also brings us to the anatomy of this cosmic bubble we live in. I mean, it is just difficult to overstate the scale of this 93 billion light-year sphere.
All right, this is our observational limit. Let's try to give you some perspective, because when we talk about how much stuff is in that bubble, the numbers just become abstract static.
They really do. Conservatively, this single observable sphere contains roughly 2 trillion galaxies.
2 trillion.
It holds an estimated 10 to the 53 kilograms of ordinary matter. That's a 1 followed by 53 zeros, and something like 10 to the 84 photons, these particles of light just constantly buzzing around inside.
And the craziest part, the origin point, this entire incomprehensible volume of matter and energy, this whole 93 billion light-year sphere, all started smaller than a grapefruit.
It's staggering. And to conceptualize how this expansion works on these scales, the raisin bread analogy is perfect.
I think this is probably the most helpful way for you, the listener, to visualize this massive stretching without feeling, totally overwhelmed by the math.
So imagine the universe is a loaf of dough rising in an oven, and we are just one single raisin embedded in that dough. As the loaf rises, all the other raisins move away from us. But they aren't crawling across the dough. They're being carried away because the dough itself space is stretching evenly.
So a raisin that's farther away from us has more dough stretching between us, so it appears to be moving away faster.
Exactly. And here's the weird, critical part. Raisins beyond a certain distance are receding from us faster than light speed.
Not because they're moving through the dough at that speed,
but because they're being carried by the stretching of the dough itself. The sheer volume of new dough being created between you and them is pushing them away that fast.
That brings us right back to the original question, though. If a galaxy is being carried away from us faster than light, how can we see it at all? How can its light ever reach us?
And that's the key. The light, the message in a bottle from those distant, supernumerally receding raisins, it can still reach us, but only if that light was emitted when the universe was much, much smaller.
It had a head start.
It had a huge head start. The light we're getting today, that 13.8 billion-year-old broadcast, came from a raisin that was close enough back then for the photon to make progress toward us, even against the expansion.
But over the billions of years that light traveled, the source galaxy was carried away by all that accumulated stretching. And now it sits at our particle horizon.
Which makes the observable universe feel almost like a transient memory, doesn't it? It's a snapshot of the universe's past that we're just now collecting.
That's a great way to put it, and it's a perfect lead-in to the implications. We've established the size of our cosmic bubble, but now we have to confront the really uncomfortable truth.
Yeah.
The bubble is not the whole universe.
Not even close.
It's just what we can see from here.
And if you connect this to the bigger picture, our observable universe is almost certainly an infinitesimally small fraction of all of reality.
I mean, the sources suggest that, conservatively, the total universe is at least millions of times larger than what we can observe.
And many leading cosmological models predict the universe is truly infinite.
Millions of times larger, maybe infinite. So everything we have ever mapped, every physical law we've ever derived, it's all confined to a cosmically insignificant bubble. That's a truly humbling dilemma for science.
It raises a huge question about physics itself. What happens beyond our particle horizon? We assume the cosmological principle holds true, that the universe is basically the same everywhere, but that assumption is only based on what's inside our bubble.
So beyond that bubble, there could be regions that look drastically different.
Absolutely. Beyond that 46.5 billion light-year limit, there could be superclusters of galaxies we can't even imagine.
Yeah.
But there's also the theoretical possibility of regions where the physical constants are completely different.
Like the strength of gravity or the charge of an electron could be different.
It could be different. We just have no way of knowing.
It's that 15th century sailor analogy, but on a cosmic scale. We're mapping a small island, drawing these beautiful, detailed charts of our 93 billion light-year sphere.
Thinking we understand the whole world.
Completely unaware that there are entire continents, maybe infinite continents, just beyond the cosmic fog.
And crucially, those regions are forever beyond our reach. The edge of what we can know is defined by the speed of light, and the space outside our bubble is moving away faster than light can travel. Information from those regions can never reach us.
It's a permanent fundamental barrier.
Enforced by the stretching of space-time.
Which leads us to the final, and I think most chilling, implication. We've established that the expansion is stretching space. But the key is that this expansion is accelerating.
Driven by dark energy.
Right. And this acceleration means our cosmic bubble isn't static. It's actively shrinking in terms of what we will ever be able to reach.
That acceleration is the true existential terror here. We talked about the particle horizon, the edge of what we can see now. But the acceleration creates a different, more restrictive boundary. It's called the cosmic event horizon.
And that's the edge of what we will ever be able to see, even if we wait forever. Can you explain that consequence? Because it seems so counterintuitive. If the universe is getting bigger, shouldn't we eventually see more of it?
In a non-accelerating universe, yes, we would. But because dark energy is forcing space to stretch faster and faster, galaxies that we can see right now.
Galaxies whose light is already on its way to us.
Yes. They will eventually cross that cosmic event horizon. The expansion of space between us and them will eventually exceed the speed of light, stretching the remaining light path to infinity before the photon can ever reach us.
They'll just wink out. They will accelerate beyond our reach and become invisible to any future observers. We're literally watching the universe erase its own history.
That is the existential bind, perfectly summarized. We are living in a very unique time where the leftovers from the Big Bang, like the cosmic microwave background, and all these distant galaxies are still visible to us. But this visibility is temporary.
So what does it look like in the far, far future?
Right.
1 trillion years from now.
An observer in our local supercluster would look up at a completely dark sky. The ancient light of the Big Bang would be redshifted so far it would be undetectable.
And every single external galaxy.
Everyone would have accelerated beyond the event horizon, redshifted into total invisibility. They would have zero evidence that the universe contained any other galaxies, or that the Big Bang ever happened.
They would think their single dark island galaxy was the entire universe.
The science we're doing today, cosmology, understanding the history of the universe, it's only possible for this limited window of time. The universe is censoring itself, leaving future intelligent species trapped in total isolation.
What's so fascinating is how the boundary of our knowledge isn't defined by our technology. It's defined by the relentless, irreversible physics of expansion itself. And that leaves you with a final provocative thought to consider.
A sobering one.
If other regions of the universe, beyond our horizon, have different laws of physics, could we ever develop a universal theory of everything that describes all of reality? Or is our science permanently confined to our single, infinitesimally small, and eventually isolated bubble?
A sobering thought indeed.
That covers 7. Ready for the next one? Let's head to fact 6.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 6, which takes us on, well, the ultimate historical journey.
It really does.
This fact fundamentally changes how you view yourself and your connection to the universe.
It's the ultimate origin story, and we're talking about stellar nucleosynthesis. You know, the concept that you are literally stardust is often treated like poetic hyperbole.
Right, like something you'd see on a poster.
Exactly.
Yeah.
But it is scientifically precise. Every single atom in your body that's heavier than helium, the calcium, the oxygen, the iron, it's all immigrant matter.
Immigrant matter, I like that.
It was forged in the violent cores of stars that died billions of years ago.
That's such a powerful stage. But let's be honest, stardust sounds romantic. How much of this story is actually verifiable, observational physics versus just theoretical modeling?
Well, it's rock-solid physics. It's verified through spectroscopy, which tells us what distant stars and nebulae are made of.
Yeah.
And through nuclear physics, which models the precise conditions needed for fusion. Our mission for this deep dive is to trace that evidence-based journey for you. We're basically providing a cosmic biography for the elements that compose you.
A biography that spans billions of years and multiple cataclysmic stellar lives.
That's the core of it. We're going to visualize that incredible timeline.
Okay, let's unpack this. Let's start with a single common element that defines life on Earth: carbon.
The backbone of life.
Exactly. We're going to trace the biography of a single carbon atom that is right now sitting in your DNA, holding the fundamental blueprints of your life. We have to rewind time a lot.
A lot. We have to zoom out and run the timeline backward, way past the formation of the Earth. So if that carbon atom is in your DNA today, rewind 4.6 billion years.
Okay.
And it was part of a massive, swirling molecular cloud, the solar nebula, that was collapsing to form our sun and the Earth. It was just one tiny piece of cosmic dust in that great gravitational swirl.
But that cloud wasn't its origin point. That carbon had to come from an earlier generation of stars, right?
Precisely. Rewind another 400 million years or so, about 5 billion years ago, and that same atom was just drifting alone in the vast emptiness of interstellar space.
Just floating out there.
Yeah, pure cosmic debris. Scattered material left over from a previous massive stellar explosion. Just a lonely speck in the void, waiting to condense.
So if it was debris from an explosion, we have to go back even further, back before the explosion itself, to find where that carbon atom was actually manufactured.
And that takes us back 8 billion years ago. Now, that atom was trapped deep inside the superhot core of a dying red giant star.
A star that lived and died before our sun was even born.
That's it. This is the moment of creation. The stellar forge itself.
So what was the environment like in that stellar core? I mean, we hear the temperatures hit 100 million Kelvin, a scale that is just impossible for us to imagine.
It's staggering.
Can you put that in context? Is that much hotter than the surface of our sun?
Ugh, vastly hotter. The surface of our sun is only about 6,000 Kelvin. The core of our sun hits maybe 15 million Kelvin. So 100 million Kelvin it's orders of magnitude more extreme. And that incredible pressure and heat is what enables the triple alpha process.
The triple alpha process, it sounds like the most precise, high-stakes manufacturing process you could imagine.
Yeah.
What exactly happens?
It's violent atomic fusion. Under that incredible heat, 3 separate helium nuclei, which are also called alpha particles.
Hence the triple alpha.
You got it. They slam together, and they have to overcome this massive electromagnetic repulsion because, positively charged nuclei naturally push away from each other. They have to fuse to create one single carbon nucleus.
You mentioned overcoming repulsion. That's such a fascinating detail, how they managed to breach that barrier. It's not just brute force, is it? There's a quantum element involved.
Yes, and this is where it gets really counterintuitive. They have to collide at relativistic speeds, but even then, classically, they shouldn't bind. What allows them to actually fuse is quantum tunneling.
Can you give us an analogy for that? Because for the listener, quantum tunneling could sound like pure jargon.
Sure. Think of it like throwing a baseball against a massive brick wall.
Yeah.
Classically, the ball just bounces back every time.
Right.
But quantum mechanically, there is a tiny, tiny probability that the ball will simply tunnel through the barrier and appear on the other side, even though it never had the energy to actually go over it.
So it just appears.
It just appears. In the star's core, the helium nuclei sometimes tunnel through that repulsive electrical barrier and stick together. And when that binding happens, that tiny, violent act of creation, it releases a burst of pure, high-energy gamma radiation. That carbon atom was quite literally forged in fire using a quantum fluke.
So we have this newly minted carbon atom trapped deep inside a star's core. Now for the delivery system. How does that material get from the deep interior of a long-dead star all the way out here to eventually become part of, us?
The star had to die spectacularly. That red giant eventually exhausted its fuel, and in its final death throes, it blasted that newly synthesized material, including our carbon atom, out into space.
At some incredible speed, I assume.
Staggering velocities, sometimes exceeding 10,000 kilometers per second. It then drifted for millions of years, mingled with other stellar debris, and eventually condensed into the material that became the building blocks of our solar system.
So we're talking about intergenerational high-velocity elemental inheritance. The entire universe is running on this massive industrial process.
That's a great way to think about it. We can visualize this with the analogy of stars as cosmic blacksmiths. Hydrogen is the raw iron ore, the simplest material everywhere.
And the stars are the forges.
They're the forges, hammering out increasingly complex elements through fusion.
That makes perfect sense. But what role does the mass or size of the star play in what they can create?
The mass of the star dictates everything. It determines the pressure and temperature it can achieve in its core, which determines how complex the elements it can forge are.
So bigger stars, more complex elements?
Pretty much. Smaller stars, like the red giant that forged your carbon, they can only get up to forging carbon and oxygen. But the truly massive stars, we're talking 10 to 100 times the mass of the sun, they can achieve much higher temperatures.
Right.
They can run more complex fusion chains, creating everything sequentially up to the element iron.
But iron is the absolute ceiling for stellar fusion, isn't it? Why is iron the critical limit, the breaking point where the manufacturing process just stalls out?
It all comes down to atomic stability. or what physicists call the binding energy curve. When you fuse elements lighter than iron-like hydrogen to helium, or helium to carbon, the process actually releases energy.
And that energy release is what powers the star, keeps it from collapsing.
Exactly. It pushes outward against gravity. But once the star begins trying to fuse iron nuclei together, the physics just flips. Fusing iron doesn't release energy, it costs energy.
It becomes an energy drain.
A massive one. It consumes more energy than it produces. This instantaneous energy drain basically steals the pressure support from the core, leading to an immediate catastrophic implosion.
And that implosion is what triggers the spectacular, world-shattering supernova.
Precisely. And that collapse and subsequent explosion is how the rest of the periodic table gets made. If carbon and oxygen are your standard issue products, well, you need a cataclysm for the really heavy, precious stuff.
The gold, platinum, and uranium.
All of it.
So those heaviest elements, they require the ultimate forge. The explosive power of a core collapse supernova, or, I think even more dramatically, the collision of two neutron stars.
That's where the R process, the rapid neutron capture process, takes over. When a massive star detonates, it releases an unimaginable amount of energy, something like 10 to the 44th power joules in a fraction of a second.
I can't even picture that number.
No one can. That massive, short-lived energy release and this intense flood of neutrons acts as the ultimate delivery truck, creating and scattering those newly minted elements, including iron, across vast tracts of space.
That brings this incredible history right back to you, the listener. The next time you hold a piece of jewelry, you're holding a piece of that cataclysmic history.
You absolutely are. The gold in that ring was likely forged in a neutron star collision, maybe billions of years ago. The iron in your blood, essential for carrying oxygen, comes from an even more violent high-mass supernova.
And the calcium in your bones.
That's from an earlier generation of less massive stars. Every part of our planet and every part of you is quite literally made from the ashes of stars that died before our sun was even conceived.
That is just profound. So what does this all mean? If our physical existence relies on this violent, billions of years long stellar recycling, if we are just reorganized stellar ash, what does that say about our place in the cosmos?
It leads to this incredible duality, this profound realization. On one hand, you have the humbling view. We are not special creations. We're not divine intervention.
We're just recycled ash.
We are reorganized stellar ash. The universe becoming conscious of itself through, random chemical evolution, an inevitable byproduct of basic stellar physics.
But the flip side of that is the empowering view. The idea that the same nuclear processes that power stars also built the exact atoms necessary for life, for thought, for meaning to emerge.
Yes. Every idea you've ever had, every moment of awareness, it's all enabled by this atomic inheritance.
It's the highest form of connection.
It is. When you look up at the night sky, you are looking at the very matter from which you were derived.
This raises the ultimate question, doesn't it? Does this elaborate, universal history make intelligent life an inevitable outcome? Or does it hint at a profound cosmic fluke?
That's the core debate. If stellar nucleosynthesis, the process of making carbon and oxygen, is universal, happening in stars in every galaxy, then maybe carbon-based chemistry in Earth-like planets are common.
Which would suggest that life might be inevitable if you have the right conditions.
It could be. But the devil is in the details of the distribution. It's not just about having the elements, it's about the ratios.
The recipe.
The recipe. You need heavy elements for a rocky planet, but you need very specific low ratios of certain radioactive elements to keep the core warm enough for plate tectonics without boiling the oceans. So if the specific sequence of supernovae that enriched our solar nebula gave us just the right mix,
that specific sequence might be an extremely rare cosmic fluke.
it might be. We might be an island of complexity because our ancestral dust cloud was perfectly seasoned by just the right generational mix of dead stars.
So we might be extraordinarily rare, a lonely island.
Exactly. Not because the physics of life is rare, but because the precise elemental inheritance required for a stable planet is rare.
Either way, the key takeaway for you, the listener, is the sheer improbability and incredible violence required for your simple existence. Every thought you think, every cell you create is enabled by atoms that survived a stellar explosion and were shaped in a furnace that hit 100 million Kelvin.
We exist because of a history of continuous, violent, high-temperature elemental recycling. Your connection to the cosmos is physical, it's fundamental, and it's ancient. It binds you to events that happened billions of years ago in distant stellar cores.
Absolutely. To wrap this profound fact up, here is a final provocative thought for you to mull over. If the atoms that make up your body are billions of years old, having survived stellar explosions and formed multiple generations of celestial objects, what does the concept of personal permanence or temporary existence truly mean in the grand, timeless recycling plant of the universe?
Food for thought indeed, next time you look up at the night sky.
That covers 6. Ready for the next one? Let's head to fact 5. Welcome back. We are moving right along in our countdown. Let's dive into fact number 5.
And this is where we really shift gears.
Yeah.
I mean, so far we've been talking about these huge, observable things. Galaxies, dark energy.
Right, things we can at least see or measure on a grand scale.
Exactly. Now we have to go all the way back. All the way down to the subatomic origins of everything. Fact 5 is, I think, maybe the most profound link between the incredibly small and the unimaginably large.
I think this might be the most mind-bending idea we've tackled yet. The concept that, that the entire structure of the universe as we know it, every single galaxy, every cluster, all those vast empty voids.
All of it.
All of it was seeded by what? Just random subatomic jitters a split second after the Big Bang?
That's the thesis.
Yeah.
So our mission here is to trace that incredible journey. We need to explore the mechanism, cosmic inflation, that took these invisible quantum fluctuations and just stretched them. Blew them up into the blueprint for the whole cosmic web. And then, we have to deal with the implications of that. The idea that our very existence is built on a cosmic roll of the dice.
Okay, so let's try to visualize this, the starting point. We're talking 10 to the minus 35 seconds after the Big Bang, that number.
Yeah.
It's so small, it's almost meaningless.
It is. It's a fraction of a second, so brief that light itself wouldn't have had time to cross a single proton.
Yeah.
So just try to picture it. You're at the very edge of creation and the entire observable universe. Everything that will become trillions of stars.
It's smaller than a proton.
Genuinely smaller than a proton. It's an almost impossible scale to grasp.
And it's not just sitting there. Right, it's not a static environment. If it was, none of this quantum stuff would matter.
That's the crucial part. This tiny, tiny volume of space is undergoing exponential inflation. And this isn't just fast expansion. Space itself is doubling in size every 10 to the minus 37 seconds. I mean, the universe went from being subproton sized to maybe larger than a basketball in less time than it takes light to cross one atom.
So everything is expanding faster than the speed of light.
The distance between points is, Though it's important to say nothing in that space is breaking the speed limit, but that speed, that incredible speed is the key.
Because if it wasn't inflating that fast, whatever was happening inside would just smooth itself out.
It absolutely would. You just end up with a perfectly uniform, featureless plasma. But the sheer speed of inflation acted like a freeze frame button for quantum mechanics.
Okay, so let's get inside that tiny ballooning space. It's not empty, so what is happening in there that creates the pattern?
Right. We have to zoom into what physicists sometimes call the quantum foam, or more accurately, the vacuum energy field. Specifically, the inflaton field that was driving all this.
The inflaton field.
Yeah, and the main thing to know is that what we think of as empty space is never truly empty. It is seething with activity.
What kind of activity are we talking about?
We're talking about virtual particles. They are constantly, unavoidably popping in and out of existence. It's a direct consequence of Heisenberg's uncertainty principle.
So there are always these little fluctuations in energy everywhere.
Exactly. Tiny little wrinkles in energy density, little quantum burps happening at the most fundamental subatomic scale.
And these fluctuations are completely random, right? They aren't caused by anything.
They are the very definition of probabilistic randomness. We're talking about tiny energy fluctuations in that inflaton field happening at the absolute smallest meaningful scale in physics, the Planck length.
The Planck length, that's 10 to the minus 35 meters. It's already hard enough to imagine that scale, but now you're telling me a fluctuation that small somehow determines the location of a galaxy that's 100,000 light years across. How do we bridge that gap?
This is where it gets really spectacular. The mechanism of inflation.
Yeah.
It stretched these microscopic quantum jitters faster than anything could possibly smooth them out.
So a ripple that should have just vanished.
It gets stretched across a cosmic distance almost instantly. The pattern gets locked in, frozen into the fabric of space itself.
So the insane speed of inflation didn't just make the universe big, it actually preserved the randomness. It was like a cosmic amplifier.
That's a great way to put it. It's like a cosmic photocopier, taking a tiny subatomic imperfection, a flaw at the Planck scale, and blowing it up to the size of a billboard.
Okay, I like the analogy of a balloon. Imagine you're blowing up a balloon, but the rubber itself has microscopic bumps and dips, things you could never see with the naked eye.
Perfect. And now imagine you inflate that balloon exponentially fast, faster than you can even think. Suddenly, those microscopic bumps are stretched out. They become large, visible wrinkles and valleys on the balloon surface.
And those visible wrinkles are the stretched out scars of quantum uncertainty.
That's exactly what they are. So when inflation finally stops, a process we call reheating, all that energy in the inflated field gets converted into the matter and radiation of the hot Big Bang.
And imprinted on this brand new universe are those scars, those ripples.
Precisely. Imprinted as these density ripples.
What does a density ripple actually look like then?
In practice, it's a region of space that has just slightly higher energy density than the region next to it. And the difference is critical. It was not a massive difference. We've measured it to be about 1 part in 100,000.
1 part in 100,000. That is an incredibly fine tuning. I mean, if it were much larger, the whole universe would have just collapsed into black holes, right?
It would have. And if it were too small, nothing would have ever clumped together to form anything.
So it's astonishingly subtle.
It is. But that tiny 1 in 100,000 variation was enough. Those were the seeds. The seeds imprinted into space-time by pure quantum randomness.
And then you fast forward 13.8 billion years and gravity gets to work.
Yep. Gravity, the great cosmic sculptor, takes these tiny density differences and just amplifies them. Over billions of years, it pulls matter into the slightly denser regions.
The rich get richer.
The rich get richer, exactly. Small lumps become bigger lumps, which pull in more matter, and eventually you get the first stars, then galaxies, and then massive galaxy clusters.
So the cosmic web we see today, the giant filaments of galaxies and the great empty voids between them, that's the literal macroscopic result of quantum uncertainty from the first tiniest fraction of a second.
That's the takeaway. Every massive object you see in the night sky owes its existence and its specific location to a random quantum event.
Okay, but if the entire architecture of our universe comes from a fundamentally random event that raises some really profound philosophical questions, I mean, what does that say about our place in all this?
It forces us to confront the fact that reality on the largest scales is probabilistic. Because quantum mechanics is truly random, the specific layout of our cosmos, the location of our Milky Way, the composition of our solar system. It didn't have to be this way.
There was no reason for the initial jitters to be arranged in a way that would lead to us. They
just happened to be that way. Exactly. If you could rewind the clock and roll the cosmic dice again, you get a different pattern of fluctuations. The seeds would be in different places.
And the galaxies would form somewhere else.
Or in a completely different arrangement. You, specifically, would not exist. This whole setup wouldn't be here.
So our existence is just one incredibly lucky statistical accident.
It's one particular outcome from a nearly infinite space of possibilities.
Yeah.
And, this is what leads many physicists straight to the idea of the multiverse, specifically infinite inflationary models.
Which feels like a logical next step, I guess. If inflation is driven by pure quantum randomness,
then it's probably still happening out there, far beyond what we can see. Our universe is just one bubble that happened to stop inflating and reheated. And in all the other bubbles, every other possible configuration of those random seeds is being realized.
So the universe we live in, the one with the density differences of exactly 1 in 100,000, where gravity is just right, it's fine-tuned by accident, by statistical selection.
That's the unnerving implication. If you have an infinite lottery, then the fact that we find ourselves on a winning ticket isn't a miracle, it's a statistical certainty. We can only exist in a bubble where the random dice roll came up habitable.
We wouldn't be around to observe the universes that are just empty, lifeless fog.
Exactly. It's called selection bias. But it does hinge our entire existence on something we can never, ever observe or verify, which is why it's so contentious.
It's still a crazy thought. We are quite literally standing on the stretched out scars of those first fundamental quantum jitters.
It's a breathtaking synthesis, isn't it? The relationship between the random and the architectural. It really makes you pause.
It does.
And it brings us to this ultimate dilemma. This is the question at the intersection of physics and philosophy. Did quantum mechanics create the structure of the universe by generating these random seeds? Or does the vast structured universe we see somehow create or enforce the very rules of quantum mechanics that we observe?
The ultimate chicken and egg problem.
It's the grandest mystery, stemming from those first 10 to the minus 35 seconds.
So we started with a speck smaller than a proton, saw how a quantum jitter was stretched to the scale of a galaxy, and we ended up questioning the probabilistic nature of our entire reality. It's just staggering. Every atom in your body is where it is because of an ancient microscopic quantum lottery.
A lottery whose outcome dictated whether the universe would be a uniform, lifeless fog or the vibrant, complex cosmic web we see today.
That covers 5. Ready for the next one? Let's head to fact 4.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 4. And this next concept is truly a wrecking ball for common sense. Today, we are deep diving into the idea that space-time itself is holographic. Now, when I say that, I mean the central premise that our three-dimensional reality, the reality we navigate every day, the one with volume, depth, and distance, is actually just a projection. It's a 3D illusion. An illusion stemming from information encoded on a distant, flat, two-dimensional surface. We are, in a sense, living inside a cosmic hologram.
It absolutely sounds like an opening line from a sci-fi blockbuster, doesn't it?
It really does.
But what's so fascinating here is that this concept, the holographic principle, it's not some speculative philosophy. It emerges directly from the most rigorous parts of physics.
Specifically for black holes, right?
Exactly. From the inescapable mathematical demands of black holes. Our deep dive today is focused entirely on understanding the nuts and bolts of this idea. Because if it holds true, it forces you to redefine what you consider reality, what space even means, and, well, perhaps even what existence is.
Okay, let's unpack this.
Yeah.
And I think we need to start with something concrete. Information storage. We're calling this the hard drive paradox.
A good place to start.
For centuries, our physical intuition told us that if you want to store more data, you need more volume. Classically, information density is proportional to the space you occupy.
Mm-hmm.
You could theoretically just keep shrinking a server or a hard drive, cramming more and more data into an ever smaller 3D volume, right? There shouldn't be a limit.
That is the foundation of classical mechanics and, our daily experience. But when you introduce gravity, and specifically when you introduce the densest object in the universe, the black hole, that intuition just shatters.
It completely breaks down.
Black holes mathematically demonstrate that there is a finite, hard limit to how much information can be stored in any region of space. And here's the kicker. That limit is not tied to the volume enclosed.
No.
But only to the surface area that surrounds it.
So black holes aren't just cosmic vacuum cleaners. They are the ultimate cosmic hard drives that reveal this strange law.
Precisely. They are the physical manifestation of the holographic limit. Everything that ever falls into the black hole, whether it's light, dust, planets, or even, theoretical quantum particles.
All of it.
All of that 3D volume of information is not stored deep inside the singularity. It's mathematically equivalent to being stored on the surface area of the event horizon.
Okay, that transition from 3D content to 2D storage is what we really need to focus on. If the event horizon is that point of no return, how does it manage to store all that complex information? Does it just smudge it all together?
Not at all. It organizes it perfectly. Think of the event horizon as a colossal two-dimensional screen.
A screen, okay.
This screen is divided into the absolute smallest possible units of physical space, what physicists call Planck scale pixels.
And just to grasp that scale for a moment, Planck length is 10 to the negative 35th meters across. I mean, that is incomprehensibly small.
It is the ultimate boundary of measurement in our current understanding. Now, here's the critical insight. Each one of those infinitesimal squares, each Planck pixel, stores exactly 1 bit of information.
1 bit.
Just a 1 or a 0. That is the ultimate physical storage limit. And what's astonishing is that the total capacity of the volume is determined only by the number of pixels on the boundary surface.
Okay, let's pause and really let the scale of this sink in because the numbers are just mind-boggling. When we look at the calculations, a black hole with the mass of our sun encodes about 10 to the 77th bits on its surface.
A staggering number.
But then if you look at a supermassive black hole, the kind that anchors galaxies, that capacity explodes to something like 10 to the 95th bits.
And that's an increase of 18 orders of magnitude based on a corresponding increase in surface area. Now, those numbers are, they're too large to feel meaningful.
Yeah, they're just abstract.
So think of it this way. What the physics is saying is irrefutable. Everything that fell into that immense 3D volume is perfectly, completely encoded on that 2D surface. The data is preserved, simply rearranged into 2 dimensions.
So the key takeaway from the black hole is that the information capacity of a given volume is not limitless, and that capacity is dictated by the area of the boundary, not the volume within.
Exactly.
It's like discovering that no matter how big a library you build, the maximum number of stories you can house is only determined by the square footage of the wallpaper covering the outside walls.
It's an almost unbelievably restrictive physical law, and it's the foundation of the holographic principle. It implies that dimension itself might be, well, superfluous when we discuss the fundamental nature of information in the universe.
That brings us perfectly to the core mechanism. How do we leap from black holes, which are extreme objects, to the idea that our mundane reality is also a flat projection? We need a mental visualization for this.
We do.
Reality is like a holographic sticker.
That's the most accessible analogy. When you hold up a holographic sticker, what do you see? You see a full, vibrant, three-dimensional image. You see depth, perspective.
And if you tilt it, the image seems to move or shift. It gives this wonderful illusion of volume.
Exactly. But if you examine the sticker closely, you know that the actual data creating that incredibly complex visual experience is flat. It's stored entirely on the 2D surface of the sticker using tiny patterns and grooves.
So the 3D experience is just an interpretation, an illusion projected from the flat data.
And the proposition is that our universe operates identically. We experience this 3D volume with gravity, depth, and movement, but the fundamental data that defines us, the chair you're sitting on and the stars in the sky, it might be flat, existing on some massive, distant 2D boundary of the cosmos.
And our perception of depth is just the readout of that flat data.
That's the idea.
It's a spectacular visualization, but scientists need more than an analogy to upend reality. What is the rigorous mathematical proof, or at least the extremely strong theoretical backing, that supports this?
Yeah.
Well, this insane idea.
Right. The crucial mathematics comes from an area of string theory called the anti-de Sitter conformal field theory correspondence. Most people just call it the AD-SCFT correspondence.
AD-SCFT.
Okay.
Now, don't get hung up on the acronyms, because the concept is what really matters.
Okay, let's treat me as a confused learner here. What does this correspondence actually prove?
It proves a mathematical identity between two seemingly different universes. On one side, you have a specific kind of universe. Let's call it Universe A, which is three-dimensional, includes gravity, and contains all the elements that make space and time work.
So, kind of like our universe.
Sort of, yes. On the other side, you have Universe B, which is non-gravitational and exists entirely in two dimensions. It's just a quantum field theory living on a flat boundary. And the correspondence says that the physics describing Universe A is mathematically identical to the physics describing Universe B.
Precisely. They are two different languages describing the exact same underlying reality. If you know how to calculate something in the 3D gravitational system, you must get the same answer when you calculate it using the 2D quantum field system. It's an intellectual duality.
It is. That's radical. If two systems, one with gravity and 3 dimensions and one without gravity and 2 dimensions, are perfectly equivalent, then what does that imply about the nature of space itself?
It leads to the most important consequence of the holographic principle. Space does not fundamentally exist.
Wait,
It is emergent.
if space is emergent, does that mean the distance between us right now, the volume of this room, the fact that things are separate and far apart, is that less real than we think?
Fundamentally, yes. If the AD-SCFT correspondence is correct, the 3D space we perceive is not foundational. It's a projection. Much like the data written on a physical DVD surface creates the immersive movie experience.
So the real physics is somewhere else.
The real physics, the essential quantum information, happens on the boundary. And what we perceive as depth and volume is just the way that boundary information manifests itself internally as an organized, consistent experience.
So the mechanism is the equivalence, and the consequence is the emergence of space and time from flat data. But why do we need this radical notion? What problem in physics is so severe that it forces us to believe we might be a projection?
It is all about resolving what is known as the black hole information problem. This is a crisis that threatens to break physics because it pits our two great theoretical pillars against each other.
General relativity versus quantum mechanics.
The two titans. General relativity, which describes the very large and gravity, versus quantum mechanics, which describes the very small and information.
Okay, let's clarify the exact nature of this conflict for everyone listening. Einstein's general relativity paints a picture where, once an object falls past the event horizon, its quantum information, all the data defining its history, its spin, its identity, is crushed into the singularity and effectively lost forever to the outside universe.
That's one side of the coin. Now, flip it to quantum mechanics. Quantum theory insists that information, like energy, is immortal. It cannot be destroyed or erased from existence.
It can change form, but it has to be conserved.
It has to be conserved. So, if a black hole eventually evaporates through Hawking radiation, as we believe it should, what happens to the memory of everything that fell in? If that information is truly lost, quantum mechanics, our most successful theory of the small scale, breaks down entirely.
So we have two completely successful, verified theories giving diametrically opposed answers at the exact same location in spacetime, the edge of the black hole.
That is the crisis point. For decades, physicists search for a way to reconcile them without breaking one theory or the other. And the holographic principle, it acts as the conceptual bridge that saves quantum mechanics without violating general relativity.
How does it manage that tightrope walk?
Well, it accepts general relativity's view that the event horizon is the maximum information container, the limit dictated by a surface area. But it rejects the notion that the information is lost inside the volume. Instead, the information never truly enters the 3D space in a permanent sense. It is instead encoded and smeared, you could say, across the two-dimensional horizon, like data etched onto a film strip.
So it's preserved, just transformed into a 2D encoding.
Precisely. The information is safe. It satisfies the conservation requirements of quantum mechanics because the data is still there, stored on the boundary. This saves the integrity of the quantum world while respecting general relativity's description of the black hole's behavior. The destruction of information is an illusion based on our 3D perspective.
That is the physics breakthrough then. An elegant solution to a massive cosmic contradiction.
Right.
But now we have to get into the existential implications because this is where it stops being just about black holes and starts being about you.
Right.
If space-time is fundamentally holographic, what does that mean for our experience of depth, volume, and free movement right now? Are we 3D beings?
That is the big question. And if we take the mathematical correspondence seriously, then the answer is, well, it's astonishing. We are not fundamentally three-dimensional beings navigating a volume.
What are we then?
We might be, at our most fundamental level, information, a complex self-aware pattern encoded on a distant two-dimensional boundary. And what you and I perceive as volume, as depth, as the passage of time, that is merely the emergent illusion projected inward from that flat informational data source.
The parallel to the holographic sticker or the DVD data projection is unavoidable here. We are the characters in the movie looking around and believing the scenery is rich and volumetric, when the true underlying reality is the flat sequence of data on the outer boundary disk.
And this realization, while perhaps not terrifying in the sense of physical danger, is certainly an absolute shift in intellectual grounding. Every experience you ever had, every memory, every thought, the feeling of walking across a room, it might all be encoded on that distant boundary.
And our consciousness.
Your consciousness could simply be the self-aware mechanism reading out that data, experiencing the illusion of volume.
It changes our entire relationship to space. We perceive separation, distance, and depth as fundamental truths. But the holographic principle suggests that these elements are derived or built from something simpler and flatter. It means the universe we see is not the fundamental universe.
We might be living inside a cosmic projection, completely unaware that the real architecture of existence resides in fewer dimensions than we can even perceive. We are fooled moment to moment by the most persistent and consistent illusion in existence, the illusion of depth. It's the ultimate efficient storage system.
And that, ultimately, is the consequence of solving the black hole information paradox. The only way out of that crisis is to assume that reality is a sophisticated, self-aware readout of a cosmic hologram. That covers 4. Ready for the next one? Let's head to fact 3.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 3. And fact number 3, well, it takes us right to the absolute limits of current cosmological theory.
It really does.
We're grappling with the staggering possibility of the multiverse, but not in a comic book way.
No, not as a cool idea for a movie.
Exactly. This is the mathematically sort of inevitable consequence of a theory called eternal inflation. And if it's true, it means our entire observable cosmos is just a tiny temporary speck.
That's right. So our mission in this deep dive is to really move past that pop culture idea of the multiverse and get into the physics that, well, that seems to demand it.
Sure.
We need to dissect the mechanics of eternal inflation and really confront the conclusion that a lot of top cosmologists now accept. If the theory holds, then everything that can happen does happen.
Infinitely many times.
Infinitely many times. And that is the ultimate challenge to our idea of being unique.
Okay, let's unpack this, because to grasp eternal inflation, You kind of have to start with the concept. It extends, right? Cosmic inflation, that ultra-rapid expansion in the first moments of our universe.
Right.
But eternal inflation says that expansion didn't just happen once and then stop. It's still happening everywhere else.
We need a clear mental model here.
Yeah.
The sources, they offer a visualization that's both useful and deeply strange.
Which one is that?
The universe as an infinitely large soap bubble bath.
Ah, okay. I like that one.
Yeah, so you have to picture the components. You've got the bubbles, and then you've got the soapy water between them.
So let's start with the bubbles, because those feel relatable. Each bubble is a separate universe, completely cut off from the others, meaning our entire massive observable cosmos.
This is one bubble.
One solitary bubble floating in the tub.
Precisely. And the technical term for that soapy water, the stuff filling the vast space between the bubbles, is the false vacuum.
The false vacuum. And that's not just empty space.
No, not at all. It's an energy state. Think of it as a region of space that's saturated with this unstable, incredibly high energy.
Like a ball resting on a high ledge.
Perfect analogy. It wants to fall. It wants to transition to a stable, low energy state, which we call the true vacuum. But while it's up there, in that false state, its energy drives space itself to expand exponentially.
Doubling in size every tiny fraction of a second.
That's the runaway expansion. That is eternal inflation.
So the distinction is critical. Inside our bubble, our universe, the ball fell off the ledge.
It did.
Inflation stopped, the false vacuum decayed into the stable true vacuum, and that released a massive amount of energy which reheated everything.
Creating all the matter and structure we see today. That was our Big Bang moment.
But outside our bubble,
The ball is still on the ledge. The high-energy, exponentially expanding soapy water is constantly creating vast new volumes of space. It's an unstoppable process.
literally creating infinite room for infinite new bubbles to form.
It's why that other analogy, the forest fire, works so well.
The nuclear chain reaction one.
Right, the fire, the false vacuum expansion, is spreading exponentially, just raging outward forever. But every so often, in a random spot, a pocket of that fire just burns itself out.
It becomes a stable clearing.
And those clearings, where inflation stops and reheating happens, those are the individual bubble universes.
Yeah.
But what's crucial is the scale. The space between the clearings is expanding so fast that they're pushed apart faster than the speed of light.
So no information can ever bridge that gap.
Never. That fractal, self-reproducing structure means eternal inflation truly lives up to its name. It never stops globally.
The scale is just mind-boggling. But what does all that infinite scope mean for, the laws of our reality? This gets us to the idea of infinite variety. It does. If these bubbles are eternally causally disconnected, what's stopping them from being completely different worlds?
Well, nothing. In fact, most of the models suggest the opposite. They suggest that when the false vacuum energy decays and a new bubble forms, the physical constants.
The numbers that define everything.
Exactly. The strength of forces, the mass of particles, they can be set semi-randomly for each new bubble.
So our Goldilocks universe, where everything is just right for life, is just one ticket out of an infinite lottery drum.
That's the statistical conclusion, yeah. And the sources give these vivid examples of just how fragile that balance is. Imagine a bubble where the strong nuclear force was just 2% stronger than in ours.
Only 2%.
Just 2%. In that universe, hydrogen atoms are unstable. They'd fuse immediately into heavier elements. Stars would burn out instantly. No complex chemistry, no water. That bubble is dead on arrival.
And what about dark energy, if you tweak that dial?
Same problem. If you have too little or no dark energy, the bubble just collapses back in on itself under its own gravity almost immediately.
Then too much.
It expands so violently that matter never has a chance to clump together. No galaxies, no stars, no planets. So you see, most of these bubbles are just failures, almost instantaneous failures.
So our own existence, the very fact that we're here talking about this, it acts as a kind of filter.
A selection bias.
We can only exist in a bubble that happened to have the winning numbers.
Exactly. It's like the fish in the pond analogy. You see a pond where every single fish is exactly 4 feet long. You might think, wow, there must be a fundamental law of fish that says they have to be 4 feet long.
But you're missing a piece of information.
Right. You then realize the pond was stocked using a net with a 4-foot mesh. You're not seeing a law of nature. You're just seeing the result of the selection method. Our universe is simply the one that fit through the mesh required for observers like us to evolve.
And this is where the science hits that philosophical brick wall. Because if eternal inflation is making infinite universes, and you combine that with the probabilistic nature of quantum mechanics,
The randomness at the heart of everything.
you have to face the most profound implication of all. Everything that can happen does happen. Infinitely many times.
Let's zero in on that link. When our bubble started, it began with these microscopic quantum jitters, just random fluctuations. Inflation took those tiny random jitters and stretched them into the massive structures we see today.
The galaxies, the galaxy cluster.
All of it. So if you roll the cosmic dice again in another bubble, even slightly differently, the initial conditions are scrambled. The whole structure of that universe would be different.
Infinitely different.
Infinitely different. If you think about every possible outcome of every quantum event, every configuration of matter, they all have to be realized somewhere in that infinite volume.
Which means there are infinite copies of Earth. Infinite copies of me.
Yes.
Wait, okay, so if there's a version of me out there who, I don't know, became a goat herder in Nepal, does that version of me feel like he's the primary reality? I mean, that's a genuine head scratcher.
It is. It creates this fascinating crisis for the idea of free will. If every choice you think about turning left or turning right results in a new reality where the other choice is just as real,
Then what weight does my choice in this reality actually have?
it completely challenges the idea of a single deterministic path.
The moment you think about an infinite version of yourself making every single bad decision you ever avoided, the concept stops being abstract physics and starts becoming genuinely unsettling.
It does. But we have to pivot back to the science here and address the biggest hurdle this theory has:
Testability.
testability. Because these bubble universes are causally disconnected, separated by that eternally inflating space, we are trapped. We are fundamentally locked inside our bubble. No information from those other realities can ever reach us.
And that's the core criticism, isn't it? It's why some have labeled eternal inflation the ultimate unfalsifiable theory.
Exactly. They argue it moves out of verifiable science and into, well, pure metaphysics.
Because you can't prove the rest of it exists.
That boundary is a huge sticking point for a lot of physicists. If a theory can explain everything, it essentially explains nothing because it makes no unique, testable predictions. But the advocates do have a few counter-arguments.
Are there potential loopholes? Any way to peek outside the bubble?
There are two main speculative ideas. One is looking for evidence of a bubble collision. If another bubble, maybe one with totally different physics, bumped into ours very early on.
Before they were pushed too far apart.
Right. It might have left a scar, a kind of identifiable low-energy remnant, maybe a cold spot or a weird asymmetry in the cosmic microwave background radiation that we could actually detect.
So that'd be like finding a giant dent on the outside of our bubble, proving something else hit it.
Exactly. The other path involves predictions about the density fluctuations themselves. While the initial quantum jitters are random, the statistical properties of those jitters might be constrained by the eternal inflation mechanism.
So it's not complete chaos. There are rules.
There could be. And if future super precise measurements of the universe's structure don't match those statistical rules, it would seriously undermine the whole theory.
So you end up with two camps. One that says, look, the multiverse just naturally flows from standard inflation, which is a well-supported theory, and another that says, I don't care, if we can't test it, it's not science.
It's a battle between theoretical necessity and empirical verification.
And that necessity, it brings us right back around to the problem the multiverse was proposed to solve in the first place.
The fine-tuning problem.
Right. If you reject the multiverse, you're left staring at this huge question. Why? Why are our laws of physics so perfectly set within this tiny Goldilocks zone for life?
It is.
Yeah.
It's statistically absurd if our universe is the only one. The odds against it are so astronomical that it really implies either a miracle or some kind of design.
And the multiverse offers a third way out, a radical one, but a third way.
It does. It completely reframes the problem.
Yeah.
It's no longer about some unique design. It becomes a statistical inevitability.
You don't marvel that a winning lottery ticket exists.
You just observe that the person holding it must be the lucky winner.
Yeah.
The multiverse explains our fine-tuned reality not through a fluke or intervention, but as simple selection bias on an infinite landscape.
So, if this is right, we are just one random, improbable outcome in a truly infinite lottery. And yet, our universe, this one bubble, it's the place where the physics allows us to even think about the infinite possibilities beyond our own horizon.
It makes our consciousness, this moment of asking the question, uniquely special in its own way.
That covers 3. Ready for the next one? Let's head to fact 2. Welcome back. We are moving right along in our countdown. Let's dive into fact number 2.
And this next one, this fact takes us out of just pure observation and, well, straight into the deep foundational mysteries of existence.
I think so, yeah.
Today, we're wrestling with one of the most remarkable and, frankly, unsettling discoveries in modern physics, the idea of cosmic fine-tuning.
That's our mission today. It's, straightforward, but also deeply mind-bending. We're going to analyze just how impossibly precise the fundamental constants of the universe really are.
The balance.
The balance, exactly. And once we get a handle on that, we have to explore the 3 major and mutually exclusive explanations for why everything seems so perfectly set up for us.
And we have to start with the core shocker, right up front. If even a single one of these fundamental physical constants were different.
And we're talking about things like the strength of gravity.
The strength of gravity, the precise mass of an electron, the energy density of empty space. If any of those were just slightly different, atoms couldn't form, stars wouldn't exist, galaxies wouldn't exist.
Which means we wouldn't be here talking about it.
We literally wouldn't be here to observe the delicate balance.
That's a staggering thought. So before we get into the why, we need to really, internalize the sheer scale of this. The source material has a great visualization for this. It says, stop thinking of the universe as some, messy, chaotic explosion. Instead, picture a gigantic, sophisticated control panel.
Okay.
And this panel has dozens of tiny knobs on it. And each one represents a single, specific physical constant.
Right, and the key insight here is that for life to exist, for complex chemistry to happen, for stable atoms, for long-lived stars.
All the prerequisites?
All of them, yes. Each of those dozens of knobs has to be set perfectly within an incredibly narrow specific range. If the strong force is too weak, the universe is just a soup of hydrogen. If gravity is too strong, it all burns out instantly.
So there's this tiny little sweet spot.
An incredibly tiny sweet spot. We call it the habitable zone, but for physics itself.
Okay, let's get specific then. How narrow are we talking? Give us the tightest one, the one that really highlights the fragility.
Let's look at the strong nuclear force. This is the glue that holds protons and neutrons together inside an atom's nucleus.
Right.
The sources detail that if you were to turn this knob just 2% higher, just 2%, hydrogen becomes impossible.
Wait, hydrogen itself, the most common element.
Gone. Protons would just instantly bind together into these non-reactive pairs. You'd have no free hydrogen left to fuel stars or, build organic molecules. No water.
So just a 2% increase basically turns the lights off in the cosmos. No fuel, no water, no organic chemistry. That's devastating.
And if you go the other way, if you turn that same knob 2% lower,
what happens then?
the opposite catastrophe. Atomic nuclei just fall apart. They can't hold themselves together anymore.
So you'd have no elements beyond hydrogen.
Exactly. No carbon, no oxygen, no iron. The entire periodic table, the foundation for everything we see, couldn't exist. So you have this total window of about 4% where chemistry is even possible.
That is an incredibly tight constraint for a fundamental force of nature.
It's just one tiny dial on that whole control panel, and it dictates everything.
So what about the biggest dial, the one that governs the structure of the whole cosmos?
That would have to be the cosmological constant. It's basically a measure of the energy density of empty space.
Yeah.
Dark energy.
This is the thing that's making the universe expand faster and faster.
It is. Now, if you adjusted this knob up, and not by 2%, but just by a factor of 10, the universe would expand so violently, so aggressively, right after the Big Bang, that matter couldn't clump.
Gravity would just lose the fight.
Gravity would lose. No galaxies would ever form. You'd just have a cold, empty, rapidly expanding void.
And if you dialed it down instead?
If you adjusted it down, the universe would have too much gravitational pull. It would collapse back in on itself in a matter of seconds.
Seconds.
Seconds, long before stars could ever ignite. The sources confirm the balance here is so impossibly delicate. It has to be accurate to 1 part in 10 to the 120th power.
Okay, 1 part in 10 to the 120. I mean, that number is so big, my brain just hears static. What does that even mean in real terms?
It's the most extreme example of fine-tuning we know of, and yeah, it needs context. If you tried to write that number out, 1 with 120 zeros after it, You'd need a scroll of paper, miles long.
Wow.
It's a number that is far, far larger than the total number of particles in the entire observable universe. Finding the right value is like blindfolding yourself, spinning a dial with that many settings and hitting the one single notch that lets the universe exist for more than a few seconds.
It makes that analogy in the sources just crystal clear. It's like finding a safe with 20 different combination locks on it. And each lock needs a number set to a microscopic margin of error. You walk up and discover that every single one of them is already set correctly by just sheer luck.
That's the scale of the probability we're looking at. And yet, here we are, observing the open safe.
So let's pivot to another analogy. We've talked about scale and probability. Let's talk about fragility. The sources bring up the idea of a championship Jenga tower.
Yes, I like this one.
It's not just about the numbers being right, it's about how they all rely on each other.
What's so fascinating here, what the Jenga analogy really emphasizes, is that the stability is systemic. It's all connected. If you change the strong force, it doesn't just mess up atomic nuclei.
Right.
It changes how stars produce energy, which changes which heavy elements get created and dispersed, which then impacts the potential for chemistry down the line. It all cascades.
So if the Jenga tower is built from these physical constants, which blocks would cause it to just instantly collapse?
Well, we mentioned pulling the strong force block. The whole periodic table just crumbles.
Yeah.
But think about the relationship between, say, the mass of the electron and the charge of the proton. If the electron were much heavier, or the electromagnetic force much weaker, stable electron shells around atoms. Impossible.
Which means no chemical bonds, no molecules.
Exactly. Chemistry itself becomes impossible. Or, like we said, shifting that dark energy block
Right.
that doesn't just make the tower shaky.
No.
It ensures the tower is either instantly crushed by gravity or just blown apart by expansion, long before you can even finish building it.
It paints this terrifying picture of fragility. We're living in a structure that, by all statistical rights, should have fallen down the second it was built.
And that profound improbability, that's the connection for you, for the listener. Against odds that make any lottery look like a sure thing, every single block in our cosmic Jenga tower is positioned just right.
For stars, for planets.
For stars to live for billions of years, for planets to form, for the complex chemistry needed for consciousness to arise. We are living in the one version of the universe that didn't just immediately fall over.
Okay, so this is where it gets really interesting for me. We've established how tuned the universe is. Now we have to ask the big one. Why?
The ultimate question.
Why are all those knobs on the control panel set to these perfect, life-friendly values? And this is where we have to confront the three major options that science and philosophy give us. And they are, crucially, mutually exclusive.
That's the intellectual gauntlet, isn't it? When you really look at the fine-tuning data, you're pretty much forced into one of these three camps. The first one, and it's the one many scientists find the most unsatisfying, is option one, pure luck.
Just a cosmic lottery. A coincidence.
We were just one. The odds were, as the sources put it, trillions to one against, but it happened. There was no deeper reason, no design, no hidden law. Just a complete fluke of chance.
It feels absurd given the precision we're talking about.
It does feel absurd, but you can't mathematically rule out an extreme accident.
But isn't that just sort of giving up on finding a mechanism? It feels like saying it's magic because we can't find the machinery.
And that's the main critique. The cost of accepting option one is this profound intellectual dissatisfaction. We just have to accept that our existence is a meaningless, unrepeatable statistical accident.
Tough pill to swallow.
It is. So if we're not willing to accept that colossal accident, we move to option two, which tries to solve that statistical problem.
Which is the multiverse.
The multiverse, exactly. This is often called the selection bias argument. The idea is that if there are infinite universes, maybe as separate bubbles from some process like eternal inflation,
Okay.
and each of these bubble universes has a different random combination of physical constants. Well, if you have an infinite number, eventually all combinations will pop into existence.
So the reason our universe is fine-tuned is just because we could only exist in one that was. If it weren't, we wouldn't be here asking the question.
That's the core of the anthropic principle,
Yeah.
yes. Our observations are constrained by the fact that we have to exist to make them.
It explains the fine-tuning problem by basically removing the need for luck in our specific case. But as the source material points out, there's a huge cost to this explanation.
A very high cost. You have to believe in an infinite number of unobservable things just to explain the statistics of the one thing we can observe.
So we're positing infinite realities that are, by their very nature, causally disconnected from ours, we can't go there. We can't get data from them.
Precisely. It's a very elegant mathematical fix for the probability problem, but it really challenges the scientific requirement of testability.
Which brings us to the third option, the most optimistic one, maybe.
And arguably the most elusive. This is option 3, deeper laws.
Okay.
This is the hope that there's some undiscovered, compelling principle of physics. Maybe an overarching symmetry, or a constraint from a theory of everything like quantum gravity that requires the constants to have the values they do.
So they aren't arbitrary settings at all. They're mathematically mandatory. The knobs on the control panel aren't knobs you can turn. They're locked.
Exactly. They're locked into fixed positions by some master equation we haven't found yet. This would be the most intellectually satisfying answer, for sure. I mean, the universe is elegant and deterministic, not random, but, and this is the critical drawback, we have zero empirical evidence for it. None. After more than a century of brilliant minds searching for a unified theory, it remains a hope. A hypothesis driven by, well, hope.
So this raises a terrifying question then. If these are the only 3 options, are any of them really accessible to science? We see the result, this perfect tuning, but we have no clear mechanism.
And that is the essential ambiguity of the fine-tuning problem, is the core of it. If the answer is the multiverse, we can't test it directly. The other bubbles are cut off from us.
So it's hard to falsify.
Extremely difficult, maybe impossible. And if the answer is deeper laws, we haven't found them. We're left in this situation where we can measure this perfect balance, but we have no clear scientific path to confirm why it exists.
So what does this all mean for you, the listener? The core takeaway here is this profound ambiguity, this existential pressure it puts on how we understand physics. We live in a universe that appears, for all the world, to be meticulously designed and impossibly precise for us.
Yet physics currently offers no clear, no testable, no consensus explanation for where that perfection comes from.
It forces us to confront an existential choice, really.
It does. Do we accept that our existence is the result of an extraordinary accident of luck? A cosmic dice roll that just happened to come up perfectly against all odds?
Or must we posit infinite, unobservable realities, the multiverse, just to make the statistics work out?
And that fundamental, enduring mystery of cosmic fine-tuning is perhaps the most challenging and deeply philosophical question that modern science has ever posed.
That covers 2. Ready for the next one? Let's head to fact 1.
We have finally reached it. The most magnificent revelation on our list. Fact number 1.
This is it. This is really the culmination of everything we've been exploring.
Absolutely. I mean, we've sailed past the cosmic shores of the CMB. We've plumbed the depths of dark energy.
And now, we're standing on the very edge of existence itself. This is the grand finale of our extraordinary journey.
We're going to challenge the most fundamental assumption there is, the very nature of what is real.
And we're diving straight into what's called the mathematical universe hypothesis, or MUH, which was proposed by physicist Max Tegmark.
Right. So our mission today is to unpack an idea that is so radical, it really flips how you perceive everything. The chair you're sitting in, the air you breathe.
Their own thoughts, even.
Yeah.
The idea isn't just that reality is described by math, as if math is some useful language we invented.
No.
It's that the universe is a mathematical structure. We are not living in a physics lab. We are living inside a giant, elegant equation.
Okay, so let's unpack that. We have to start with our gut feeling, right? For most of us, when we think of math, we think of something abstract. That old thought experiment. Picture a perfect circle.
Right. It exists only as an idea. Infinite points, all equidistant from a center. It's ideal, it's perfect, but it's not physical.
Exactly. And then I look at my hand. And that feels physical. Real. It's made of atoms, energy.
The circle is an idea, the hand is reality, that's the instinct. But what Tegmark says is that this distinction is, it's an illusion. It's generated by observing the structure from the inside.
So the core concept we have to get our heads around is this. What if my hand, my brain, the entire universe are literally mathematical objects?
Not approximations or descriptions.
The thing itself.
The thing itself, exactly. I mean, think about what matter is. We drill down, right? Molecules, atoms, then electrons and quarks.
The fundamental particles.
For a long time, physics treated them like tiny billiard balls with properties like mass and charge.
Right, little bits of stuff.
But modern physics doesn't see them that way. Not really. It treats them as points in a field defined entirely by their relationships and how they obey certain equations.
Okay, hold on. I'm going to be the skeptical proxy here for the listener. If the universe is just math, where's the mass? Where's the stuff? You telling me the weight of my phone isn't real?
It's real, but the stuff part is the illusion. The mass of an electron, for example, it isn't some tiny bit of physical material. It's a parameter. It's a number in an equation that defines the electron's relationship to the Higgs field.
So a particle is just where all these mathematical relationships intersect.
Precisely. The universe is built of these relational structures, entities defined entirely by their rules and connections, not by some non-mathematical substance underneath it all.
Okay, that makes the library analogy you mentioned so much clearer. So if reality is math, where does that math exist?
It exists timelessly in a sort of vast library containing every possible consistent mathematical structure. And consistency is the key.
So if a structure can be written down logically without contradicting itself,
Then it exists as a reality. Whether it's a structure where 2 + 2 = 4, or maybe a much stranger one where 2 + 2 + 5 is internally consistent because of its own weird rules.
and our universe is just one book in that library.
A specific book, yeah. It's a structure defined by its axioms. Gravity follows an inverse square law. Particles have these exact mass ratios. We have 3 space dimensions and 1 time dimension.
But the book isn't the instruction manual for our universe.
No, it is our universe. The math doesn't describe reality. The math is reality.
So time, space, matter, energy, all of it just emerges from the relationships within that mathematical entity.
Yes. And suddenly, that grand old mystery of why math is so ridiculously good at describing physics it vanishes.
The unreasonable effectiveness of mathematics.
Exactly. It's not a miracle. It's effective because the physical world is the math. They're the same thing.
Okay, this is where we have to bridge that gap from pure abstraction to my personal experience, right? If I'm just math, how do I feel anything? How do I perceive physicality?
And this is where the video game analogy really helps. It's the perfect lens.
Right, so imagine a super realistic video game.
Hyper-realistic. Inside the game, a character feels gravity. They feel consequences. To them, it's a physical reality. But if you step outside the game and look at the server, what is it?
It's just code, information,
Yeah.
algorithms defining mathematical relationships.
Exactly. And we, inside our game, think we're made of particles. But those particles are just the basic variables in the code. My body isn't made of tiny bits of material. It's a fantastically complex mathematical pattern, a subroutine.
A subroutine that's observing itself and its own rules, which of course leads to the big one, consciousness.
Right. If the universe is code, what are we? The MUH suggests consciousness isn't some separate non-physical thing.
It's not magic.
It's simply what a sufficiently complex, self-processing mathematical pattern feels like from the inside. We are a subsystem within the structure that becomes self-aware.
That is deeply counterintuitive. It implies that consciousness isn't special to biology, it's a feature of complexity.
Yes. Any sufficiently complex mathematical structure could, in principle, contain observers. We aren't separate from the math. We are the math reading itself.
Okay, but if we're just patterns in a static structure, what about free will? If the whole universe is one timeless equation, then all the steps are already written. How can I choose to do anything?
That's probably the deepest critique. And Tegmark's answer is that we experience the illusion of choice. From the outside, all moments are fixed.
Like frames on a roll of film.
A perfect analogy. But from our internal viewpoint, which is all we have, we perceive a flow of time and we make decisions. The experience of being the self-aware pattern tracing a path through that fixed structure feels like free will.
So free will is the feeling of our complex mathematical code running its course.
It's unsettling, I know, but it is internally consistent.
And this connects back perfectly to fact number 2, the fine-tuning problem. We wondered why the universe's constants were set just right for life.
And this answers it. The only reason we find ourselves in this specific, life-friendly book is because the mathematical structure that defines us as observers can, by definition, only exist in a structure that allows for observers.
The ultimate selection bias.
Yeah.
We're asking the question because the math allowed us to exist to ask it.
Exactly. And if this is all true, if every consistent mathematical structure exists, that has an immediate, unavoidable consequence.
The level 4 multiverse.
The level 4 multiverse. And this is a huge leap from what we've discussed before.
We talked about level 3, the idea of parallel bubble universes from eternal inflation. But this is something else entirely.
It's a quantum leap in abstraction, literally. Level 3 universes share the same fundamental math, just with different outcomes. The level 4 multiverse means every consistent mathematical structure is its own independent reality.
They don't even need to be in the same space-time.
Or any space-time at all. These aren't just parallel Earths where I chose a different breakfast. These are completely separate realities with different rule sets.
So you could have a universe where 2 plus 2 plus 5 is consistent because its fundamental logic is different.
Precisely. Or a universe with 10 spatial dimensions. Or one where gravity gets weaker with the cube of the distance, not the square. They exist simply because their internal math doesn't create a contradiction.
And we don't perceive them because we're characters stuck in our book. We can't step outside and look at the whole library.
The observer is constrained to the reality defined by its own mathematical laws.
This brings me to the question that gives me real pause. Where does math itself reside? If it's not in space or time, because they're part of the math, where is it?
A crucial question, and this is where Techmark leans heavily on Plato. He suggests these mathematical structures exist in a Platonic realm.
Not a physical place.
Not physical at all, an abstract realm of existence. The structures are real, but they're non-physical. They don't need a substrate to run on. They don't need space. They don't need time. They just are. Timelessly and eternally.
That feels like a massive philosophical leap, though, doesn't it? Just to make the whole hypothesis work.
It is, but consider the alternative. If math only exists when it's physically realized, you have to ask why our specific physical version was chosen. And you're right back at the fine-tuning problem.
The creator
Or
problem.
creator problem. By making them Platonic, the need for a chooser vanishes. The math just exists. Our universe is just the self-aware part within one of those structures.
So if the universe is a static mathematical object frozen outside of time, it didn't really begin. It won't really end. It just is.
It is. Think of it like a four-dimensional block where every slice is a moment in time. You, the listener, are a continuous pattern traced through that block.
So my past and my future aren't gone or yet to happen. They exist simultaneously, permanently.
They are permanently fixed in the mathematical structure, yes. What you perceive as the flow of time is just your consciousness tracing its predefined path through that static architecture. The flow is an internal feeling, not an external reality. And that's the final mind-boggling implication. If the mathematical universe hypothesis is true, you have always existed and you always will. You are a permanent, eternal feature of the mathematical landscape.
You are literally immortal. Not because you come back to life, but because your pattern is just permanently there.
Encoded forever in the timeless architecture of pure mathematics.
That is the grandest possible way to conclude this dive. What an extraordinary journey this has been.
It's been incredible. We started this countdown, this analysis, way back at fact number 10 with the cosmic microwave background.
The first whisper of the universe. Then we went to the violent hearts of galaxies, supermassive black holes at number 9.
And then the mystery of dark energy at number 8, pushing everything apart.
We took in the sheer scale of it all at number 7, the observable universe, and traced ourselves back to exploding stars with Your Stardust at 6.
We saw how everything came from tiny quantum fluctuations at 5, and then questioned if it was all a projection with the holographic principle at 4.
We wrestled with the level 3 multiverse at number 3, and then the sheer improbability of our existence with fine-tuning at number 2.
And now, fact number 1, the ultimate explanation that ties it all together, that the universe is mathematics, and we are the self-aware patterns living inside it.
Thank you so much for engaging with us, for completing this extraordinary journey of knowledge.
We really hope these deep dives give you a new framework for thinking about your place in all of this.
If you enjoyed this deep dive, make sure you subscribe so you don't miss the next one, custom tailored just for you. Thanks for listening to the Extraordinary 10 podcast.